Hello everyone, my name is Professor Wilson Kamami and my YouTube channel is also called Professor Wilson Kamami. This is where we simplify mathematics together. So this is our second video on set theory. The first video we looked at the introduction to sets. Now today we are going to look at sets operation. So continue watching and subscribing for more videos as we simplify mathematics together. So at the set operation you realize that at this one, we are going to look at the union of a set. Just a hiccup of what we did last time. We said if you have set A, which has 1, 5, 7, 9, and you have another set B, 1, 6, 8, and 10, we said if you have these two sets, we said how we name set, it should be in capital. The elements are enclosed using curly brackets and are separated by commas. That's what we did. So now when you look at the union of a set, we start with the first one, union. We use capital, that one, that is the symbol for union. So if you are looking at the union of a set, A union B is a set of all elements both in A or in B. That's why we use the word all. Are in A or in B. A or in B. And remember, one thing we said when we are naming set, we say that it has distinct objects, so you don't repeat a number twice. So in that case, we will have 1, 5, 7, 9. So those are the sets in A or in B. In B we have 1. We cannot repeat 1 because we said set has distinct objects. So we add 6, 8, and 10. So this is A union B. Set of objects in either in A or in B. That's why we like using the word or. A or in B. So that is the word that you mainly be using when you see this symbol of union. A or B. So it's a combination of all those sets, those elements which are either in A or in B. Again, if you have to use the Venn diagram that we were showing, it is if you have A and you have B, don't mind my drawing, there are those sets, those elements that are in A, this is my A, and all those elements that are in B. So if you have to know that one, this is A union B, all elements in A or in B. Let's look at now the second one, the intersection of sets. Intersection. The intersection we use this symbol. So when we talk of intersection, just like the way I said we use mostly all, in this one we use edge to mean intersection. So if again I'm going to use the same example, that's why I have no clap, A and B. So it is A and B. So it is a set of all elements that are both in A and B. A and B. So it is a common. So which elements are there both in A and B? It is, I think, only 1. So we will have 1. That is the intersection. Intersection. Elements that are in A and B. That's why I use the word add. Those are, so in case, again, if you are to draw this one in a Venn diagram, we look at, that is A, that is set A, this is set B. This is our universal set. So the intersection is the point that of elements that are both in A and in B. That's what we call the intersection. I want to emphasize on those two. The union is elements in A or B, so you combine them. But again, you don't repeat an element because we say the set is of distinct objects. When it comes to intersection, you realize that when it comes to intersection, there are elements both in A and B. So they must be those elements that are appearing in A and also they are appearing in B. We call them we call that one intersection of a set. Now let's look at the other one that is a bit different. We look at what we call complement. maybe we can look at the third one. The operation is complement. Of a set. So when we are looking at a complement of a set. Let's assume you had a universal set of odd numbers between 1 and 10, from 1 to 10. That is 1, 3, 5, 7, 9. That is our universal set. Remember, in our previous video, we defined what is a universal set. What is a universal set? Assume now you have a set A, which have maybe 1, 5, and 9. So these are elements in A, but whenever we talk of A complement, these are elements in A. I want to define it. If you have a universal set U, set A having that element, A complement, there are those elements that are not in A. Get that one? Not in A, but are in what? Are in the universal set. As you can see, in our universal set, we have 1, 3, 5, 7, 9, and our A has 1, 5, 9. So A complement, there are those elements that are not in A. A complement, not in A, but you find them in our universal set. What are those? Now you get it is 3 and 7. That is the A complement. Again, you might be having B. B has 3, 5, and 7. So what is my B complement? B complement, there are those sets that are those elements that are not in B, but you find them in our universal set. They are not in B, but you find them in our universal general set under consideration. So again, what is B complement? We have 1, but 3 is appearing, 5 is appearing, 7 is appearing, so the other one is 9. I want to make that one clear. When we talk of complement, they are not in A, not in B. So when we are talking of A complement, they are not in A. B complement, not in B, but you find them in the universal set. So the other set operation I want to look at it is the set difference. Maybe we look at the fourth one is set difference. Now we are going to look at set difference, but before set difference, I have talked about the complement. When we talk about complement, this is our universal set, and assume we have an ordinary set A. So if you are to represent in a Venn diagram, this is the A complement. This is those elements that are in universal but are not in A. This is what we call A complement. So now this is our set. Maybe I can put here. This is our set A. So these are A complement. So that the A and A complement, when the union of it, you have the universal set. So the fourth one is set difference. Set difference, we use that symbol, minus. Assume you have two sets, A and set B. A minus B, there are those elements that are in A but are not in B. In A but not in B. There are those elements. Whenever I talk of object or element, you know I'm referring to the same thing. So there are those elements in A but are not in B. So maybe I can leave a space to explain in a Venn diagram. When I have B minus A, there are elements in B but not in A. So if you have a Venn diagram, assume you have two sets, ordinary sets, set A and set B. So when we are talking of A minus B, they are already we have set A, but you minus those ones that are in B. A difference B, so it is this part. So you don't include those elements that are already in B. Again, B minus A, we have two ordinary sets, A and B. A and B. This is our universal set. So there are those elements in B but are not in A. But you remember, at this point, we put those elements that are both A and B. So it means that it is this part. This is the B minus A. So when you are representing in a Venn diagram. Let's take an example. Assume you had a set A has 1, 5, 7, 8, and 9. And maybe you have set B 1, 6, 8, 4, 10. Those are two sets. We have two sets, A and B. So you realize that B minus A, we start with A minus B. There are those elements in A but are not in B. You realize 1 is there but is in B, so you ignore that one. 5 is there but is not in B, so one element is 5. 7 is there but also is not in B. 8 is there but also is appearing in B, so you don't include. Then the other one is 9. So that is A minus B. Again, if you are to look at B, now B minus A, there are those elements in B but you don't find them in A. Like in this case, you find that 1 is in A, so you don't include that one. 6 is not in A, so the first element is 6. 8 is in A, 4 is not in A, and 10 is not in A. You realize there are those B minus A. So 1, if it is here but it's already in A, you don't, that is not B minus A. So you include those elements that are in B but not in A. And if you are to draw that diagram, a Venn diagram, remember we represented everything in a Venn diagram. You realize if you had this is A, this is B, you have A and B. When you are drawing a Venn diagram, I always advise students to start with the common elements which are appearing both in A and B, or what we call intersection. What is appearing A and B? We have 1, we have 8. I think there are only 2, if I'm not wrong. We have 8. Now here we have A minus B. Or you put the other elements of A minus B, you find it, you have 5, 7, and 9. Those are 3 elements. Again, here we have 6, 4, and 10. As you can see, if you are to look at the Venn diagram, this was A minus B, you have 5, 7, 9. This was B minus A, you have 6 and 10. And when you look at A union B, if you are remembering what we covered, A union B, they are all elements. So you have 5, 7, 9, 1, 8, 6, 4, 10. We say the order doesn't matter, but you find that we have all the elements. Now if you have A intersection B, there are those elements that are in A and B. We have seen already we have 2 elements which are common in both cases, which is 1 and 8. So that's what we call set difference. We have looked at the other union, intersection. We have looked at the complement. Assume we had a universal set. Now, our universal set was between 1 and 10. Assume that was our universal set. So, what is A complement? There are those elements. A complement. I'm just doing a recap. A complement are those elements in A. They are not in A, but you find them here. So 1 is 1. So you start here 2, 3, 4, 5, 6, 8, 10. Those are A complement. They are not in A, but you find them in our universal set. B complement. They are not in B, but you find them here. So we have 2, 3, 5, 7, and 9. You can cross check that one. They are in B. They are not in B. B complement, not in B. So you find that 1 is not in, is in B. So it is 2, 3, 5, 6 is there, 7 is not, 8, then 8 is there, so you have 9. So that is B complement. So the last part of what we have looked at complement, we have looked at the set difference, we have looked at the intersection. Now we are going to go ahead and look at what we call the symmetric of set. So we now look at the last part of symmetric difference. Symmetric difference, we use this symbol. So A symmetric B, it is A union B minus A intersect B. Or you can say it is A minus B union B minus A. Whatever you want. In simple terms, we are joining the A minus B with the B minus A. So if we have to use the Venn diagram, it is this part. Yet you don't include the intersection. You ignore this one. You ignore that intersection. There are those elements in A and B but are not shared commonly. They are not shared by A and B. There are all those elements, like if we take an example we had here. Let's take our example. We can have another example. We had a universal set of 1, 3, 7, 9, 11. And we had set A had 1, 7, 9. And set B had 3, 7, and 9. So we are talking of all elements that are in universals in A and B but are not shared commonly. So what are those? So A symmetric B, we will have 1, 3. I hope it is clear. There are those elements in A and B but are not shared commonly. So if you are to represent that one in a Venn diagram, if you are to represent this one in a Venn diagram, we have A set A and B. Let me write here inside A and B, and we have our universal set. So A has 1, 7, 9. So we have 1, 7, 9 is common, and then we have 3, 7, and 9. You can see 7 and 9 is common in both cases. As we said, A symmetric B, this part and this part. So you find you have only 1 and 3. And then you remember we had 1, so those elements that are not A in B or B, we have 1, 3, we have 11 here outside. So that we have 1, 3, 7, 9, and 11 is not in A or B. So that is the operations of set. I think that marked the end of our second video on the sets operations. Now, just a recap, we are supposed to look at the set operations. That is the union of a set, intersection of set, the difference, the complement, and the symmetric set. So in that case, symmetric difference, and in that case, that marks the end of our second video on sets operations. I would also like to look at the third video. Our next video will be on Venn diagrams and how we apply the Venn diagram. That one will apply either in business student, wherever you are. Where do we apply this sets theory? How do we apply Venn diagram in solving our day-to-day problems? So thank you very much. Continue subscribing, and let's continue simplifying mathematics together.